This tutorial is sponsored by Squarespace, which makes making websites actually easy. In this tutorial, we're going to try to solve a problem that is seemingly simple, but you scour the internet and there's not a fucking solution for it, at least for Blender. And before I keep ranting about how there's no solution, let me show you what the problem is. So, in Blender, I want you to imagine a scenario, and this is a scenario you will encounter, but let's say you have a cube. Simple example. You hit edit mode, you hit X to delete, and I'm just going to delete the edges and faces, okay? So I have a mesh, and I've reduced it to only vertices. The question is, how do I go backwards? If I only have vertices, how do I go back to a mesh? And this seems like a silly question, right? I select this, I hit F, I select this, I hit F, and we slowly construct this. But you see how this becomes an issue as we get more points. And let's say I wanted to do it all at once. I select all the points, I hit F. It does not know what to do in this scenario. And there's all kinds of fills. We just use the normal fill. We could try fill holes, doesn't work. There is not a simple solution for this problem. Now, why does this problem matter? I want you to imagine that you're like either motion tracking and now you have a bunch of 3D points in space you want to connect, or maybe you have a point cloud because you're doing some kind of photogrammetry and you want to connect it. And in that scenario, you end up with a model that's more like this, but again, just the point cloud. And this is a scenario where kind of going one by one is not feasible. Now, I hit F to make a triangle, and I can kind of like visualize how to construct this, but if like a simple like 300 polygon thing is going to take me this long, how is this going to scale? So we are going to what is called skin a point cloud or make a surface for it. Now, some of you might know if you're tech heads that there is, or math heads really, I don't know what head you'd have, probably a game developer head. You might know that there are some algorithms for this, namely Delaunay triangulation. This is a triangulation, again, you're making triangles of a point cloud. It's a triangulation that has some properties that make sure all the triangles play nice, whatever. The most popular algorithm for this problem is something called the ball pivoting method, and that's also hard to implement. So how do I take this and just hit F and get it to work? That's what we're going to be talking about. So as you might expect, this is a GeoNodes problem. So I'm going to make a geometry nodes, and what we need is at least a very basic algorithm to get us closer to skinning a point cloud. Now, we're going to make some assumptions. The first assumption we're going to make is the way that we want this skinned, because this is valid. It's just not the one we want. The first assumption I'm going to make is the kind of skinning we want is kind of like the natural one. So you can see how I'm kind of doing this manually, and you would probably generate the exact same skinning. And I need to ask myself, how do I know which triangles to make? It's kind of like I look at what points are near each other and wouldn't make triangles that are too thin, okay? So the first assumption I'm making is that my triangulation should kind of follow this rule where nearby points form triangles, okay? You could have that not be the case, but that is what we want. And the second assumption we're going to make is that we don't have any extra information. We just have points. We don't know their normals. We don't know anything, okay? So what's the algorithm going to be? As you might expect, if we're going by the assumption that nearby points should be connected, we might want to start by selecting nearby points and just making edges. Okay, so that's step one. And we do that a bunch of times. Okay, so how do we do that? Well, luckily, there's a good node for this. We want to find the nearest vertex of a vertex. We're looking at a vertex, and I'm saying which one is the closest. We want to look at it and connect there. Well, luckily, there's a node for this. It's called index of nearest. What it tells us is the index of the vertex that is nearest to the one we're looking at. Well, if I take this index and I evaluate at index, okay, so I'm saying look at this index of the closest one, and I look at the position vector, well, now I know the position of the nearest point. So if I am on here, it would probably generate the position of this one to be the nearest, for example. Now, why does this matter? Well, if we have both the original position and the nearest neighbor position, we know the instructions how to make an edge between them. Now, Currently, there is no nice F button that will do this for us, so we have to get clever. How are we going to do this? Well, if we take our points and we instance an edge in some sense, so I'll show you what I mean. I'm going to make a mesh line. A mesh line looks like a line, in other words, an edge. And we instance this. That scream kind of sounded like the Chop Suey one, like, wake up. I'm going to make a mesh line, okay? And I'm going to instance it. Well, now every single point, you can kind of tell, has a edge connected to it. Now, you can kind of see where I'm going with this. If each one has an edge, we just have to orient it so that it's going towards our nearest neighbor, because right now they're all going upwards, and they should be the correct length. Well, starting off with the correct length, that's actually pretty easy, because if we're looking at a source point and we know its nearest neighbor, the length of this edge should be exactly that. It should be the distance between these points. How do we calculate that? Well, we take the position of the nearest neighbor, and then we just calculate the distance. And luckily, all we need to do is plug that in. So all of a sudden, we get something more reasonable. So this is without, this is with. So some edges are longer than others, and as you might expect, the edges up here, where the points are more spread out, are going to be bigger than the edges over here where the point cloud is very dense, as you can see. Second thing we need to do is we need to orient these edges. We need to orient these edges such that they're pointing in the correct direction. Well, this is also easy. What you do is you compare the destination position, the nearest neighbor, compare that to the original position, and we are going to subtract these. So what does that mean? That means that if we're looking at a point and its nearest neighbor, I want this vector, the one that points from the original to the nearest. And that happens to be this vector where we take, it's kind of like the reverse of what you think. You take the nearest one and subtract the position of the one we're looking at. If you're curious why it's this and not the other way around, the reason is the position vectors of both of these are relative to the origin. So I have the position of the first point and I have the position of the second point. And when I subtract these, basically what I'm saying is I'm saying take this vector, the one that leads to the nearest neighbor, and then add the inverse of this vector. Add this, and those instructions together make an arrow pointing to the left. That doesn't really matter. But now we have a vector pointing from one to the other. That is actually not enough, as you can see. It does reorient stuff, but not correctly. That's because this is a vector, and we need rotation information. This is what a line Euler to vector is. It takes a vector, like this one, and outputs a rotation. So I'm going to plug that in here and hit Z. It just so happens to be Z. So you can see point cloud, edges. So I think at one time or another, each of us has had a reason or an idea to make a website, and maybe we didn't do that because making websites is hard, except it isn't with the sponsor of this video, Squarespace. Squarespace makes making websites as easy as like dragging around squares or blocks to assemble your website with text blocks, video blocks, whatever you want. And here are 3 features of Squarespace that might interest you. First of all, comes with its own analytics suites, so you know who is going to your website, where they're from. 2, it comes with its own asset library so that any picture, audio, whatever you upload stays over there in the cloud. And 3, like I said, you can just drag around blocks as a means to design a website. You can inject HTML if you wanted to, but you don't need to get so complicated. So head over to Squarespace to make your website, and when you're ready to take that thing live, use my link in the description to save 10% off your first purchase of a website or domain. And now, back to the tutorial. Now, this is actually doing a pretty good job, but couple issues. First of all, it's not connecting all the edges. Obviously, we're missing one here, etc. Second of all, if you think about it, if I have a set of, let's say a set of 2 points, well, the nearest neighbor to this one is going to be the other, so we form an edge. But then the nearest one from the perspective of this one is now the other, so we form a second edge, and now we have them overlapping. So we're making extra edges, and additionally, consider that we have, so that's an issue. We have overlapping ones, and then kind of consider the possibility that we have a third point here. Well, this one's the nearest neighbor, but from the perspective of this point, this is the nearest neighbor. But we never end up getting this connection here because it's just not close enough. And I do want that connection because it will form a triangle. So what I'm saying is nearest neighbor kind of works, but it's not giving me enough variety. Well, there is a nice solution for this. Notice that the index of nearest, which tells us which vertex, the index of it, is the nearest one, it has something called group ID, and this is what we're going to exploit. Group ID is basically saying, let's say I have a bunch of points and I want to find their nearest neighbor. I could put these in collections. So here I've made two collections. I will call this group A and group B. What the group ID does is it says, yes, find your nearest neighbor, but only within this group. So even if I had to point right here, such that obviously this is the closest one to this one, right? It is. We can't use it because it's in a different island, so it would give us this one. So what I'm saying is the grouping will give us different nearest neighbors than what's actually there, which is exactly what we want. So what I'm going to do is for the group ID, I'm going to separate them into, I guess, two groups. You could do multiple groups, but I think this will be most efficient. Take a random value, get a Boolean, which basically says either 0 or 1. In other words, we have two groups. And just connect that here. And you can see that gives us a different result. But more importantly, as I change the seed, I think you can see where I'm going with this, okay? So the seed is going to give us a different edge connection. Now, also, just a technicality, what we have here is a bunch of instances, so I want to make sure to realize them so we have geometry. And second of all, like I said, some nearest neighbors will be each other's in the sense that there will be two edges. We want to reduce this, so we are going to merge overlapping points. So you can see before we had 1,000 points, now we have 500. So almost roughly half of them are the nearest neighbors to each other, or maybe a fourth of them. Don't need to think about that. Okay, so this is kind of our approach, but the question, of course, is how do I get not just this filling, but also this one, and this one, and this one, and combine them? Well, we do just that. We do all of those, and we combine them. So I'm going to take this. I'm going to hit Control-G to make a node group. So you can think of this node group as maybe like form edges. Okay, that's what this operation does, without with. I want to do this a bunch of times, except if I do this over and over and over again, I guess it does kind of do something. But each time I want to use a different seed value. So inside this node group, connect the seed, and now we can control that seed. Okay, and more specifically, what I want to do is I want to do this multiple times. So we are going to use the repeat zone. Now, one thing I just noticed is that I'm using an old version of Blender because I do VFX for this company, and they like to use 3.6. If you're watching, change that. Okay, so I'm just going to call this edges. All I need to do, sorry, I keep hitting the mic. All I need to do, look at that. This is what I watch. All we need to do is open up a version of Blender that's recent. This one should be long-term, not long-term support. This is like the current version of Blender. All I need to do is I need to take this and then open up the same file. Okay, so nothing's changed, except this time we have the repeat zone. So repeat zone goes here, it goes here, and then in between, I put this node. So all that's changed is now I can do this operation multiple times, except this isn't what we want either. We want each iteration to kind of join with the previous one, so we kind of accumulate stuff, right? Okay. So what I basically want to do is I want to form this, but then kind of like join it with like a previous collection in some sense. So let's think about how to do this. So I'm going to put a second socket. This may or may not be what we want to do, but we'll think about it. And we want to join geometry from this one to this one right here. So let me tell you what I'm thinking. What I'm thinking is we have some source geometry. So that's going to be Suzanne. That gets fed in here such that each time it's going to form a edge kind of grouping, and then it's going to repeat. Now, of course, it does seem like we have a problem here. And that problem is that I don't actually want this. Okay, so what I'm doing is I'm saying I have a point cloud. In this case, it's Suzanne. That gets fed in here. We do calculate the edges, but notice that this geometry gets fed right back into itself. That's because I never want to change it. But in the background, we're also calculating this kind of like edge formation, which we join with our previous one. So we're going to kind of accumulate them. So this is going to be our point cloud, but this is going to be our edge thing. Okay, now they're still not accumulating, even though we are joining them. Now, the reason that this isn't working the way we currently have it is, yes, we do have a changing seed, and yes, we can do a lot of iterations. Let's do 22, I guess. No matter what seed we pick, and they can change. That's a good thing. We're doing the same seed over and over and over again. So yes, they're joining, but it's like joining the same thing. So we don't get any progress done. So what we actually want to do instead is we want to make sure for every iteration, all 22 of them, we get a different seed. So just take this right here, and I'm going to add 1 to it. What is he thinking? What is he doing? I'm going to add 1 to it and feed it into itself, such that we now have a parameter that is equal to, well, here's the arrow. It's equal to 0 on the first iteration. Then, and this will be the seed, so the seed will initially be 0. Let's go back here. The seed will initially be 0, but then we add 1 to it, feed it back in. Now the seed will be 1, 2, 3, and we join it each time. So you can see, as we add iterations, now we're getting more of a complete picture here. Now, again, this isn't like a perfect algorithm. This is more of a naive algorithm, but it will give us better results than what we would have had if we just hit F for fill, which would have not given us results. So you can kind of see how this gives us a pretty good start, and this will be better the more points there are in general. But if I do 50 iterations, we're pretty confident that we have most of the triangles, and what we want to do is there clearly are too many vertices, and that's because there's still a lot of overlap, so I'm going to do a final merge by distance, and now we get something like 505 vertices, which if we, or 2,000 edges, which if we look at our monkey, is fairly close. I guess there's double the amount of edges. And I guess that's because here we're doing a triangulation, whereas this has quads, right? So if I was to take this and run it through a triangulate, now it has closer, not exactly, but closer to 2,000 edges. Here we clearly have extra. But the point is, we're getting somewhat close, okay? What we want to do now is I'll make a second copy. Is there's still no good operation for filling, and yes, you could try the fill curve approach, but it's not going to work. We can apply this, and now we have a new mesh that if I hit F to fill, it's not great, but it is better. Now, this result is going to get better and better and better the more points there are. I mean, you could just keep hitting F for fill and try mixing this with like different algorithms like fill holes, but in general, but you can see we're getting closer. So how do we get even better? Well, first of all, before we do that, how do we get even better without adding more geometry? Well, in theory, all we need to do is we merge by distance, but just kind of increase this, which will get rid of some geometry, but will make it less chaotic, such that when I apply this and now I hit F for fill, we're getting a much more complete filling. So again, naive approach, but it does kind of help. But a more realistic scenario, of course, is we have more geometry. So let me do that. Let's say we have a Suzanne. I'm going to subdivide it, maybe even twice. I'm going to hit apply. I'm going to delete all of this. So now only edges and faces. So now we have quite a dense point cloud, and this is more realistic in the world of photogrammetry. Now, when we use our thing, we get quite a dense triangulation. And again, you can play with these settings to get different results. You hit apply, you go to fill mode, or you go to edit mode, you hit fill, and now we're getting something much more full. Yes, there are still issues here, but now kind of like fixing this manually is less like insane, right? This gets you 80% of the way there. Now, of course, I still do not want to fill any of this in manually. So you're going to do that by hitting F a couple times, and if that generates errors, what you want to do is you want to play with these numbers over here. So play with the iteration count. I don't think you ever need more than 20, and play with this merge by distance until you get something a bit more acceptable. But depending on your use case, this could still be plenty, unless you want like a perfect mesh. But you can see we're getting a bit closer, and there are methods like using the... There's a good add-on for this. I'm trying to remember. I think it's called like the 3D printing add-on. May or may not help. So if I go to add-ons, I go to 3D print. Nope. Is there something just called print? Yeah, 3D printer toolbox is what I was thinking of. There's an add-on that lets us do certain things. Like we can hit check all, and it will see everything wrong with our mesh, and we could try to like clean it up and make manifold. This actually solves quite a few of the issues, except, of course, we lose detail in the ears. So it's a give, and it is a take. But the nice thing is you can always like play around with these settings and see what those settings do. So I understand that this is a naive algorithm and is not an implementation of the ball pivoting algorithm, which I might look into. I read about it, but I didn't get to the point where I'm like, yes, I can now make this in Blender. It's not as robust as the ball pivoting method or Delaunay triangulation, which kind of gives you a tetrahedralization. It makes tetrahedra instead of triangles. It does that, which isn't really what we want. But again, it's a good start. You could always use multiple of these geometry nodes modifiers to kind of fill in the holes and then join those together. So it's kind of like you're taking a random sample, which you are. You know what? Why end here? I want to try that idea. So I'm going to do this, and you could take... I mean, I guess is taking more samples kind of the same thing as what I just said? I don't know. But what I was saying is you could take two of these geonodes and like do fills on both of them, and then in all likelihood, let's say we have a triangle missing here. Now, if I take this add and make it like add 3, which will give us a different triangulation, now, I forget where that triangle was. Maybe it was like here. Now that's filled in. So, again, I'm kind of squirming because it's not a perfect method, but it is better than nothing. And isn't that all we want in this life? Okay. Anyways, if you want this Patreon file of kind of like a naive triangulation algorithm of a point cloud, which runs pretty damn quickly, by the way, that will be available on Patreon. And more importantly, if you join the Patreon, you get access to every Blend file I've made and made available over the last 4 years. There's a library of exclusive tutorials. Honestly, I made those a while ago. Sometimes you get early access to tutorials like this one, in theory. And in general, it is the main funder of this channel, of this YouTube channel, realistically. But that doesn't have to matter to you. You can just buy the things, and I could sell the things to you. So, Patreon link somewhere, and yeah, that's the deal.